All right, thank you. Good morning, everyone. So yes, I'm going to talk to you about the WFIRST mission at large. So not only microlensing, but the other sides of the mission. My expertise actually on the coronagraphic instrument that's going to be on board WFIRST. I'm the deputy project scientist for the coronagraph instrument, which means that I had to ask a lot of help to present the other side of the mission. So I'd like to thank here Jason Rhodes, Olivier Doré, Scott Gaudy, and Matthew Penny for providing relevant material. I've been trying to get you the latest instrument design, latest scientific yield estimations, but if some of you know of more recent different estimates, please let me know. Okay, so just to start, coming back to 2010, it's kind of interesting to see that WFIRST was not an existing mission concept submitted to the decadal review. So in fact, we could say that WFIRST is a creation of the decadal committee, which basically saw 3 mission concepts arrive, which all needed about the same kind of aperture, the same kind of wide field imaging capabilities in the infrared, and basically merged them together. And these 3 missions were JEDEM, which is a dark energy mission, MPF, which was the microlensing planet finder proposed by David Bennett, which is really exoplanet census. So you guys are more familiar with that side of the mission. And then NIRS, which was an infrared all-sky survey that was proposed by Daniel Stern, also in answer to the decadal request for answers. So anyway, the decadal was pretty smart about it and said, well, maybe we can get 3 times the science with the same instrument, so let's just recommend this as our highest priority, and that's what they did. And in that way, we can say that WFIRST really checks many boxes. So it was the #1 in space, large-scale priority, addressing core science questions in dark energy and exoplanet science. It also covers many other science goals which were described in this 2010 decadal review. I'll let you read them here. Yeah, gravitational wave astrometry is not going to be done with WFIRST. I'll give you that one. Okay, and so another piece of good news that happened later was that the WFIRST project inherited a larger telescope. So instead of the 1.3 to 1.5 meter telescope envisioned by the decadal, turns out that the US National Reconnaissance Office donated the WFIRST project a 2.4 meter telescope to be repurposed for astrophysics and wide field imaging, just looking up instead of down. Okay, so the good point here is that this telescope is already built. It's still sitting in a storage facility not too far from here, actually. And that added just one more science case, or one more interesting tech demo that could be done with the WFIRST coronagraph. So not only did it improve the science yield that you would have gotten for the other science themes with a 1.5 meter, but it also made it possible to include now a coronagraph to image exoplanets, because now you get the right spatial resolution to have a chance at it. So that's just a cartoon view of the coronagraph, and I come back to it. So if I come back to the previous slide, I can just add one more check here, which is that now WFIRST also addresses the #1 in space, medium scale priority of the decadal, which was to prepare for a planet imaging mission in the future. Okay, so now moving on to the overall science goals of the mission, and there are mostly like 3 types of major science goals. The first one is to characterize the history of cosmic acceleration and structural growth to constrain the nature of dark energy. And that's, of course, the purpose of the wide field instrument 2 surveys, the high latitude survey and the supernova survey. And I'll get back to these. Another goal, general science goal, is to understand how planetary systems form and evolve. That's, we've been saying that for, I don't know, 30, 40 years. But there are really some observational benefit of doing a microlensing survey of stars in the galactic bulge, looking for anomaly created by planetary companion around the land stars, and we're going to get back to this. I'm only going to touch upon this subject a little bit because, of course, Matthew is going to describe that in more details right after me. Then these science goals which are related to direct imaging of exoplanets and exoplanetary systems with the coronagraph. I'll get back to this in detail. And finally, I want to insist on the fact that even during the 5 or 6 year nominal mission of the WFIRST project, the plan is to have a GEO program which will have roughly 25% of nominal time associated to it. And then if the mission is extended, it could be 100% GEO. We all hope the mission would be extended past the nominal 5 years. That's the same, but in a more visual way. And Jason Rhodes tell me that roughly the size of these boxes is roughly the consistent with the time spent on all of these different surveys. So we got the wide field imaging surveys, the microlensing sensors, the coronagraphy, and the guest observer program. Just what I described before. Okay, so let's just start with the dark energy side of the mission. And then here the main goal is to really make some progress and move away from this very humbling chart that you can see here, which basically is saying that we don't know about 95% of the matter or energy of the content of the universe. Roughly our estimate is like 27% of that is coming from dark matter, and maybe 69% from dark energy. But really the questions we are trying to answer here is cosmic acceleration caused by a new energy component, dark energy, or is it really just due to the breakdown of general relativity on cosmological scales? If type 1a supernovae have a luminosity that are not strictly constant but could change when you look at the more distant universe, for instance, that could be an issue. And then the second question is, if really the cause of the cosmic acceleration is a new energy component, is this energy density constant over space and time, or has it evolved over the history of the universe? So these are very top-level questions that the mission will address, and in order to differentiate between these two scenarios, the WFIRST wide field imaging side of the mission will try to determine two things: the expansion history of the universe, and in that case, the observables are supernovae light curve, Microlensing images, and baryon acoustic oscillation techniques, all at redshift up to Z of 2. And the other thing that's being constrained by whether dark energy or other modification to Einstein gravity are at play is the growth history of the largest structures in the universe, which you can measure using, again, weak lensing, but also redshift space distortions and galaxy cluster techniques. So that's the overall goal of the mission for the wide field imaging side. And how is it made possible? Well, it's made possible by the extraordinarily large field of view, instantaneous field of view that's coming with the WFIRST, which is about 0.4 by 0.8 degrees, and it's covered here, by these maps of H4RG detectors. There are 18 of them. So that's your instantaneous field of view. If you want to compare to HST, basically that's the same image quality roughly as you would get with HST, but over exactly a 200 times more important field of view. And so, for instance, for the imaging and spectroscopy side of the mission for the high latitude survey, the total field of view is going to be covered over the 5 years of the mission, 2 years for that particular survey, is of the order of 2,000 square degrees close to the South Galactic Pole. And you can barely see it here, but in comparison are the field of views of some of the HST most common instruments. And you can see in comparison how much larger the WFI field of view is. Okay, so in order to separate between those two scenarios, if we keep going, now the requirements are that the WFI should be able to detect at least 10 million galaxies spectroscopically over a redshift range of 1 to 2 to be able to measure their redshift. And that's addressed by the high latitude survey, and the current predictions meet the requirements by quite a bit. You can see it, here. The other measurement that's supposed to be done is to measure the shape of this of over 100 million galaxies, and that's also planned to be done with the high latitude survey, largely. And then finally, in terms of the supernovae survey, the requirement is to measure the light curves of at least 2,000 supernovae at redshift at least one, and that's going to be covered by the supernova survey. And once again, the predicted capabilities are above requirements. Okay, so, and a little bit more details about how this is going to be done. So this is a view of the wide field instrument, which is really split in two optical channels. There's the wide field channel per se, which has this large field of view, special resolution of 110 milliarcsecond per pixel, which is almost like we sampled at 2 microns. So not only do you have a very large field of view, but it's almost diffraction limited in terms of pixel size. The image stability is absolutely fantastic, and that's also something we're going to be benefiting on the Coronagraph side, and that's really coming from the design of the telescope. That's pretty amazing numbers. I remember WFIRST was designed to work in Earth orbit to be stable with a variable thermal load. We're now talking about having WFIRST at L2, so we expect the stability to be even better there. Sorry. Okay, so near-infrared bandpass, 0.76 to 2 microns. The 6 imaging filters, that's the latest numbers I have for them. They may have changed. There's also going to be a GRISM for multi-object medium resolution spectroscopy. And that's all for the WFC. And then for the integral field channel, IFC spectrograph, will be 2 fields of view, one for the supernovae follow-up of the supernovae detected by the WFC, and then the galaxy photometric redshift calibration unit. Okay. All right, so moving on now rapidly to the microlensing side of the mission, and once again you hear a lot more about it. But the main objective here is that the WFIRST microlensing survey will carry out a statistical census of exoplanetary systems in the galaxy from the outer habitable zone to free-floating planets, which is the first time it will ever be done, including analogs to all of the planets in our solar system with the mass of Mars or greater. That's going to be done, obviously, by monitoring stars toward the galactic bulge. Just to step back a second and say, why do we care so much about exoplanet population and demographics? Well, it's because despite a lot of progress and efforts over the last decades, we still don't fully understand planet formation. The planet distribution function may have the physics of planet formation imprinted on it, which is why we're interested in them. Pending migrations and a lot of other mechanisms that may have impacted the distribution of the system since its formation. So that's why it's hard. We know that the planet distribution function depends on many parameters, at least 4 of them: planet mass, planet period, stellar mass, stellar metallicity, plus a mass-radius relation that depends on this parameter. Furthermore, and that's the main point here, we must piece together all of this multi-parameter distribution function via different observational methods, which all have their different selection biases that have to be properly taken into account if you want to retrieve the underlying true physical populations of planets. So you need to get rid of all of these biases. So an important point, obviously, is that if you look at the WFIRST microlensing search area, it really extends maybe from the outer habitable zone to the outer regions of the system, and that's absolutely complementary to the very central zone that was addressed by Kepler. For Kepler, we are really interested in the base case in planets within the orbit of Mars, around M stars, around G-type stars. For small planets, we are really limited to the orbit of Venus. So there's a very nice complementarity here in terms of search space and what we can learn from microlensing versus what we could be learning from transit measurements. And that's, of course, well shown in Matthew's plot here, which has been pretty famous now, which really shows the very small overlap. There is some overlap between the two techniques, but really one is limited to small separation and one addresses large separations, even free-floating planets. And that's the WFIRST microlensing survey. So, as we said here, and then here are the latest predictions for the science field of the microlensing survey, about 1,000 planet detections, 120 with Earth mass and below, 14 with Mars mass, and hundreds of free-floating planets, including 16 with Earth mass, if each star had one. So that's pretty impressive. Okay, just a few more words about the advantages of doing microlensing with WFIRST. 7 different fields will be monitored of 0.28 degrees square each. The cadence is really important because each of these fields will be monitored every 15 minutes, and it is commensurate with being able to sample the short amplification anomalies caused by planets. They're typically an hour or 2 or 3 long, and in order to be able to disentangle between the different parameters of the system, the mass ratio, the separation, you really need that kind of fine temporal sampling and high precision at the same time. And that's what WFIRST will provide. So yeah, that's the point here, that high precision photometry on short timescale enables detection of weaker signals, basically smaller planets, and in the habitable zone. In the habitable zone means they are short in time. And here is a view of what field of view will be covered by the WFIRST microlensing survey close to the galactic center. That's the 7 different fields. So remember, each of them is 0.28 degrees square, so that's a pretty big field of view. And I think that Matthew had an example of a detection already made in that field with other instruments. But I will let him talk more about that. Just to give you an example of the type of detection that can be made. There will be hundreds of these. All right, so now moving yet to a different side of the mission. So microlensing will address statistical information about planetary populations. Now we're moving to characterization of the atmosphere of individual planets, which is another side that we're of course interested in. So the WFIRST CGI promises to start getting into that new regime where we're going to be able to detect planets in scattered light. So let's just look at this little plot here, which is the usual plot of direct imaging that really shows the flux ratio of the planet to its host star on the y-axis versus separation here. These little red dots here are where we are standing now from the ground, imaging self-luminous planets. So pretty far from their star, because they are young enough, they are still emitting light from their original contraction, so they are still pretty bright even though they are far away, so they are ideal cases for direct imaging from the ground. Where we want to be in the future is in this region here, and these little black dots are the model or simulated, expected, I should say, flux ratio in the visible for known RV planets, Jovian planets. And you can see there's about a 3 orders of magnitude gain or increase in difficulty, if you will, from 10⁻⁶ contrast with respect to the star to about 10⁻⁹. And that's what you need to be able to do to get to Jovian planets in scattered light or around mature stars. So now the planet is not emitting thermally anymore, it's just reflecting starlight. So the WFIRST CGI is designed to do the first direct optical imaging and spectroscopy of known RV planets, Jovian planets orbiting mature sun-like stars. We have a list about 20 of them. It will also search for previously undetected planets around nearby stars. And you're saying, well, don't we know about all of the Jovian planets around the nearby stars? We don't. For early type stars, RV measurements are not possible at high precision. In some cases, the orientation of the system is just not right for RV. And planets about below a Neptune mass and further than 1 AU have not been detected by RV so far for most of them. And so they should show up in these blind searches with the CGI. Another science goal is to image faint debris disk structures analogous to our own solar zodiacal light. We expect that the CGI will do very well in this, with sensitivities about a few times that of our solar system zodiacal dust. And what's important here for those of you who are familiar, for instance, with the LBTI 10 micron survey, is that these measurements are going to be in the optical. They are the first measurements of faint debris disk structures in the optical, which is really important for future missions. And as much as we like to learn from what's happening in the thermal infrared, it's only telling you limited information about what's happening in the optical in the absence of proper model for the grain distribution sizes or albedo, etc. So I think that's an important science goal that's not been really highlighted too much so far, but that's guaranteed with this mission. And then finally, we're going to be also characterizing protoplanetary disks, so gas-rich disks younger than 10 meg/year with this high spatial resolution space-based mission. Okay. It's just a pie chart of where the observing time would go with the CGI, so the different science goals I just mentioned. So that's in months, and that's assuming 1/6 of a 5-year mission, which is exactly 10 months. You will hear me say that the mission nominally is 5 years or 6 years. It kind of keeps changing, so I'm not sure exactly what it is right now. But here this assumes just a 5-year mission and a total of 10 months of CGI science. Okay, so I took to this already a little bit. We hope not only to detect planets, but to see also the resonance structures in the zodiacal disks around them. And that's an important design parameter for future missions. I mean, depending on the level of dust emission in these systems, you may need a different telescope diameter. So here, this is a simulation that's been done by Chris Stark that shows basically the science-y, the number of exoplanets of Earth size that you might be able to detect with future missions as a function of the telescope diameter. There's plenty of hidden assumptions here, but the main point is if you fix yourself a certain goal in the number of exoplanets you want to detect, that will take a different telescope diameter depending on how bright these zodiacal dust clouds are. And that's what we need to know. Right now we have an upper limit of 60, which is going down slowly, but we're interested in knowing how low this is. A little bit about the technology of the Coronagraph. So really what's going to enable these measurements is these complex optical systems where you basically block the starlight with a series of masks, either in the focal plane or in the pupil plane. Is what you would do for disk science. So we have a number of different modes for the WFIRST CGI, which have been actually successfully tested in the lab. Sorry, come back. Yeah, so these are actual lab measurements. So you get the residual starlight still at the center, and then you have what we call a dark hole, where you basically null the star by a factor of 1 billion. And so if you had a planet there, you would be able to see it at about 1 billion to 1 flux ratio. I'm happy to answer more questions about this. So here we have another Coronagraph arrangement which has a larger field of view, which allows you to look at debris disks and even exo-Kuiper belt analogs, which are a bit further out in the system. Okay, so the other science goal, of course, is to do for the first time also a spectroscopy of a few or maybe 10 extrasolar giant planets in scattered light. And here is a view of what different planets would look like at different separations if we were to look at them with a noiseless instrument, just degrading the resolution to 50. So you can see like the methane feature, the water vapor feature, and you can see how dramatic the change would be, for instance, if you were to bring our own Jupiter from 5 AU to 0.8 AU. So there's a lot of physics there that changes when you change the separation and the type of cloud that will condensate, and that change the reflectivity of the planet, etc. So we're going to be able to try and check these physical assumptions about atmospheric composition and some of the WFIRST CGI team members have started to look at that. We're going to access these 3 bands here with R equal 50 each of them. And that should allow us to start to do some parameter retrieval. Here's a simulation of the type of parameter that you may hope to retrieve from such observations. That's work by Roxana Lupu. And she just shows here the posterior PDF of key atmospheric parameters. Can't remember exactly. So I think it's the methane fraction. Some have to do with the surface gravity, pressure, opacity of the cloud, etc. But that's the kind of end product that we could hope to get from these observations. At least constrain the abundance of methane. I think it's pretty clear that we would be able to do this, and that can be used to determine the bulk metallicity of the atmosphere. And in that case, we would be using a slightly different arrangement with an integral field spectrograph after the coronagraph. That would cover about 18% bandwidth at once with R equal 50. And we would walk through 3 filters to cover the whole spectrum. Okay, so maybe another aspect of the CGI, which is not scientific but has a lot of importance in the preparation of future missions, is the fact that the CGI can be really seen as a tech demo for future missions. And I tried to show this here, where you can see a number of new technologies which will be either pushed to new limits or tested for the first time in space. So the Large Ultra-Stable Space Telescope and Observatory, that's alluding to the fact that for the CGI to work, you need some kind of passive stability at the order of 100 picometer RMS level, which has never been measured in space, and which is very hard to model with accuracy. Another aspect is the low-order wavefront sensing and control. We're going to be using DMs in space for the first time with a lot of actuators. There are some new chronographic masks. Ultra low noise photon counting visible detectors, EMCCDs, that will be flown with WFIRST, and also validating some image processing techniques which are supposed to allow you to detect planets below the residual starlight level, which we know work from the ground but have never been pushed to this kind of levels. I just want to insist on one of them, which is the low order wavefront sensor, which is this thing that's going to wiggle now. Yeah, that's this thing here. And basically that's using starlight, natural starlight, to correct the wavefront in real time at high frequency for tip tilt. We're talking about line of sight pointing better than 10 times better than what HST does, roughly. So anyway, that's for the tech geeks in the audience. Sorry that I'm spending much time on this, but that's going to be a big deal to demonstrate that in space. I don't think anybody can seriously think of launching a big mission like LUVOIR or HEBEX without having this intermediate step. So that's major in my mind. All right, so as a summary, and to show you also a bit of a nominal DRM for the whole mission, the WFIRST mission is the top priority for the identified from the 2010 Astrophysics Decadal Survey. Since that recommendation was made, we also inherited a larger telescope, which is Hubble-sized and with exquisite optics that allow you to get a very large field of view, about 100 times larger than Hubble with the same type of resolution. This provides unprecedented science capabilities in many different areas: dark energy studies, exoplanet population studies, general astrophysics enabled by very wide field near-infrared surveys, spectroscopic and imaging. And as I mentioned, it also will allow to test coronagraph at contrast levels compatible or consistent with what we need for future missions, maybe just a factor of 10 away, but 1,000 times better than what's ever been done from the ground so far. In terms of the DRM and the split of the time of the nominal mission, At the moment, and it may change a little bit, but the idea is to spend about 2 years for the high latitude survey, imaging and spectroscopy of that large field of view that I mentioned before. It's going to be about 6 months for supernovae type 1a search and follow-ups. About 1 year for the coronagraph, 1 year for the microlensing survey, and about 1.5 years for the guest observer program. And once again, an extended mission will consist of an expanded GEO program. And all data should be public days after they are taken. I want to see that. It's going to be a challenge. Okay, and then to finish, I just wanted to mention here the names of a number of scientists who are responsible for different sides of the mission, and invite you to contact them if you have any specific questions about the dark energy, the microlensing survey, or the coronagraph. So here are the people you want to be talking to, and very clearly WFIRST is your mission. It's going to fly in 10 or 15 years, and you'll be the ones doing great science with WFIRST. I'm going to stop here. So yeah, I didn't mention that at all. The project has been asked by NASA to look into the accommodation of a Starshade. So we don't know yet if a Starshade will fly as a Starshade rendezvous for WFIRST. That recommendation, if it comes, will come from the decadal. But NASA has instructed the project to make the coronagraph and its optical train compatible with operation with a Starshade. In particular, that means being able to acquire the Starshade with a guiding camera, so we can, align the Starshade and the telescope on the line of sight to the star. So that's where we stand right now. I think it's been budgeted, just the accommodation, to about $20 million. So, some of that money will have to be spent by 2020, but the policy has been to not order any of the parts before we hear from the decadal.
What would be the capabilities?
The capabilities would be, in principle, much higher throughput than we get with the coronagraph. So, some optimistic DRMs predict that we should be able to detect Earth-like planets. If we are lucky enough, there are a few around the nearby stars. Oh, that's fantastic. That's great news. Well, if all of our nearest systems start to be very favorable, like Proxima and Tau Ceti, that's good news.
Other questions for Bertrand? If not, thank you, Bertrand.